Hey everyone, long-awaited second screen cap of fMRI analysis in SPM12. I'm going to continue on from our last session and show you how to set up a first level analysis in SPM12. So if you've just launched MATLAB, and if you just make sure that you are in our folder, so if you go here and navigate to the common area, fMRI analysis sessions, and then you'll find yourself in the current folder where our data lives from that we've already pre-processed. So first of all, if you want to launch SPM, just type in SPM fMRI. To launch. Might take even longer if you're running it on Jupyter. Okay, so we get our graphics window, our menu, and our progress bar. We launch the batch editor to set up our first level analysis. So if you want to navigate to SPM, Stats, fMRI Model Specification, you add that module here to the module list. Now, first of all, you set up the directory where you want your first level analysis to be written. So you select directory, specify, and we'll navigate into first level. And I have created a new folder in our first level file called ScreenCap, which is where I would like this version of my first level to be written. So just select it on the right hand side there. Remember this, the left hand side of this directory selection is for navigating, the right hand side is for selecting. Once you selected it, it turns up in the bottom, click done. And that's where we're going to write our design to. Now, first you need to put in some timing parameters. So the first thing is units for design. So this is if you have the onsets of your various task conditions in scans or in seconds. You need to select that here. And now the onsets for the task that we're analyzing, we have here in an Excel file. And we can see we're interested in modeling these decision time points. And you can see that these are here. These are in seconds. So we're going to choose seconds. Now it also wants some scanner parameters, which you'll remember from our pre-processing steps. So first it wants to know the interscan interval, so that's the time taken to acquire a single volume. So it's 0.72 seconds for our data. And the micro time resolution is the number of slices. In our scanning acquisition parameters. And then the microtime onset, because we have a multi-band sequence, we pick the middle slice. And because we want to pick somewhere in the middle, because with multi-band sequences, the beginning and end is less clear because they're requiring multiple slices at the same time. Now, for data and design, this is where you want to put in your smoothed data to apply your first level conditions to it. Select new subject session. And in the scans field, you want to specify the smoothed data that we did at our pre-processing stage. So we'll select pre-proc, and I'll go for my copy one backup, run one. And you see in here are all the different types of files that were created by the pre-processing steps. Now, in order to filter this, so you'll just pick up your smoothed data, you type in SWAU, press enter, and that will only show you the smoothed pre-processed data. Now, you can see here it says the file name and number one. So in order to select, you've got 612 volumes that were required over time for this imaging run. So you want to type in enter, and then all of the frames will show in the selection. Right click that, click select all. Now, so there's a couple of different ways that you can enter in your conditions, which are the things that occurred over the course of that scan, and you want to enter the onsets of them. Now, the first way that you can do it is you can just enter in the conditions. So you would go to conditions, new condition, and say what we first want to do is we want to model approach decisions in our approach avoid paradigm. So we can see here, these are the decision time points. This is what the choice was. So if you go to your Excel file and you just select by approach, filter it by approach, then you've got all of your approach decision time points. Copy those. Condition, name, onsets. Paste in the values you copied out of the Excel sheet. And then for duration, so you can have, in some designs, stimuli are turned on for a number of seconds in more of a blocked design. So you would say the number of seconds which the stimuli were on the screen for. Now, in this specific task was more of an event-related design, so the stimuli were quite quickly changing on the screen. So therefore, we put our duration down as 0. Just click specify and 0. So that will model the approach decisions. Now we can do the same for avoid. So we go condition, name. So this is still the same functional data that we've, these 612 files. We're just applying the different conditions that occurred. So if we want to model the avoid condition, we would type in avoid. The onsets, so we go back to our Excel file. And select approach and select avoid. Onset times. I paste them in there. Durations, again, these are fast stimuli that aren't turned on or off for more than a few seconds. And so there are 2 conditions that we would want to. Now, there are obviously other conditions in this task, but for simplicity's sake, these are the 2. And so you can see that's how you would put them in. Now, there are other, we will look at more sophisticated movement reduction programs we can use. But for now, we'll stick in a multiple regressor, just a regressor, which is created by our pre-processing stage, and this takes account of movement. So if we go regressors, specify, regressor, oh no, if we get rid of that regressor, we want to call it a multiple regressor. So you specify that you want to specify a file. If we go to our pre-processing stage and copy one back up, run one, and we have here our RP text file, and that's automatically created by the pre-processing stages, and it takes account of puts the movement parameters in as a regressor. So if we select that, and now there is this art regression, outliers and movement is the more sophisticated one, which we will put in, but I'll come to that after I've shown you how to run art to do this. So click done. And just to show you those movement regressors, so when we carried out our first level and our pre-processing, there was a PS file created, and this is the PS file here. And you can see that these are the movement parameters. So it takes account of when the head moved in the X, Y, and Z direction, also when it rotated. So that RP file that we just selected contains those movement parameters, so that they will be included in the model as a regressor. Okay, so we'll leave the defaults there for now, and we will specify this model. So you just click Run Batch. can see in your MATLAB window, it's calculating here. So running fMRI model specification, saving the design, and just calculating. You can see our little thermometer is telling us when it's complete. Okay. Oh. So we can see our design here in the graphics window. So you can see here where we modeled these approach decisions. You can see when these occurred over time. So if we look along here, these are our scans. So our individual volumes of data that occurred over the scanning run. It was from 1 to 612 volumes. And then you can see that this is when the approach decisions happened, which are the values that we copied and pasted from our, from our Excel file, those onsets, and similarly for avoid. This is our design, and you would review this design after you've specified it and ensure that none of the conditions were overlapping. In that case, you would see grey boxes here that would tell you that you hadn't uniquely specified one of your conditions. Now, these regressors are the movement regressors I was talking about. So this would be our X, Y, Z movement translation, and these would be our rotation parameters. They also put a constant in to the model as well. So that's one way how you would set up your first level analysis. However, you can, if you think about having lots of different subjects and lots of different conditions, you can see how manually copying and pasting your onsets in would result in a lot of human error. So I'm going to show you a more automated way to enter in these contrasts, which will lend itself better to scripting. So the first thing that you need to do is you need to create an SPM multiple conditions file. Now, this will require a little bit of MATLAB coding, which I won't go into now, but I'll just show you the structure of the file. So if we navigate to folder, we see this mat file here, AAC run 1 onsets. So I'm just going to load that. This mat file has 3 elements inside it. So it's got, which are standardized and must be called the same thing in order for MATLAB to, in order for SPM to recognize it. So we have names. These are, so the various conditions. Approach decision, avoid decision, approach feedback, avoid feedback, approach reward, and avoid reward. So you can see your 6 conditions. And then onsets. And in each of these, so it's nested underneath the onsets of each of these conditions. So onsets for 1, which is the first, those are the onsets for the approach decisions, and the onsets for the avoid decisions are in here, and then the onsets for the approach feedback, avoid feedback. So you can see how copying and pasting these might have led to a lot of human error. So that's the format of your multiple conditions file, and I'll show you how you enter it into your first level analysis now. So if we go back to the batch editor, we'll use the same directory. We can just overwrite the SPM file that's already there. You see we've got units, seconds, interscan interval 7266 and 33, the same as before. Scans are also the same. We're going to look to the same smooth functional data. However, this time we're going to get rid of these manually entered conditions. So we'll delete condition 1. And there's no conditions. And what we do instead is we select this multiple conditions field, and we specify, and I'll just show you that we're in copy 1 folder where the onsets mat file is that I just showed you. Select that, click done, then we will run this batch. So when you've already got an SPM file written to a folder, it will always come up with a warning saying the current directory contains an SPM file, continuing will overwrite. Say, well, a lot of the time you would have done that by mistake, so stop would be good. But in this case, we are happy to overwrite it, so we'll press continue. We just have to wait. You can see our thermometer counting up. You see our old design file in the graphics window, but we should see that overwritten with the new one. Now, so you can see our design file has been overwritten with the new one, where we see our approach decisions, avoid decisions, approach feedback, avoid feedback, approach reward, avoid reward. And these happen, they almost look like they're at the same time, but they are, if you think about it, like the approach decision is quickly followed by the approach feedback, and they are actually uniquely specified. They don't actually occur at the same time. So we can see we've got our additional conditions in here, and then our movement parameters, which we left in from the time before, and our constant. So we can see how we would estimate the model using the multiple conditions map file. Now, once we're happy with how the model's been specified, we want to estimate it. So we would stat estimation. Model estimation. You can set a dependency on that to your SPM map file, and then you can actually, you would normally put these two things together. For this, I think I will delete that module so that we don't re-specify it, and I will just instead have model estimation. Rather than a dependency, I will specify, and I will choose screen cap, and that's the model that we've just specified. That's this, what we see in the design, in the graphics window. Select that, and then we click run to estimate it. So that's taking your design and actually running the statistics on it. It might take a little bit more time. Switch your thermometer. Just wait a little bit. Maybe leave this running, go make a cup of tea, come back. The computer's doing the work for you. We can actually look at the folder while this is all going on. And so where I specified the model, now it will be writing these new images. So these resols and beta weights. The beta weights are the coefficients of the regressors that we are putting in to explain all of our imaging data. So we've got x equals the final result, which is all of the imaging data, and then we have a regressor for each condition that we've put in to the model to explain that data. So is almost finished. It's just estimating the parameters, making those files. We can review it. And it's done. So we can see in our folder, we've got, so those results were kind of temporary files that were used to calculate these final beta weights. But these final beta weights represent the conditions that we entered into the model specification and our movement parameters as well. So that's why we have 13 of them. So we have our avoid decision, approach decision, avoid feedback, approach feedback, approach reward, avoid reward, and then 1, 2, 3, 4, 5, 6 movement parameters. What it also produces is a mask image, which you can just open and look at in MRI run, where you can see which voxels were visible for this person. So you can see your dropout in the orbital frontal cortex here. And we can do some remasking on that, which I'll show you at a future date. You can see the dropout there in the different depending on where someone was lying in terms of their sinuses in relation to the magnetic field. Anyway, so once we've estimated our model, we can look at the results. So if we click on results button, and we can refer to our design. Click done. And you see here we have our contrasts. So what you would want to do here is you want to set up contrasts. So you've got your approach decision, you've got your avoid decision, you've got your approach feedback, you've got your avoid feedback, and what we're really interested in is the differences between those conditions. So just as an example, we'll set up the contrast of approach minus avoid. So we want to look at which parts of the brain were active in the approach decision, whilst controlling for which parts of the brain were active in the avoid decision. So if we put in a 1 for the approach decision, so if we look across here, we have our conditions that we entered in. So if we put in 1 for the approach decision, minus 1 for the avoid decision, and then it will fill with zeros till the end, so that we're only contrasting those two things. So I'll call it approach minus avoid. And then we can also define another contrast if we wanted to look at the other way around. We could look at avoid minus approach. For that, then we would look at minus approach plus avoid. Now, it's important that these contrasts add up to 0, so that you're controlling for one of the conditions. Okay. And so we have these two contrasts defined. Here, when you click on the approach avoid one, you can see it's plus approach minus avoid. Over them and click, you can see. And then avoid minus approach, you can see is minus and plus. So you click done when you're finished, and then it will give you options on how you want to run these stats. Now remember, we're just running this on one person, but this is just for just to visualize how you can see where the brain data comes from. So we will apply no mask here, and we will you can choose whether you want to do FWE correction, which is the most conservative, but for the purpose of just looking at one person, we will say none. And we will look at a p-value. We'll look at a stat. You kind of, when you're looking first, just put a standard of 0.001. And then, so that's the threshold for the p-value of the individual voxels. You'll only show voxels which pass this level of significance. And then you want to put another threshold on there too, where you say, we only want to look at clusters of more than 20 voxels. So we're not interested in just 3 voxels that are together. And seeing as this is just one person, let's be a little bit more liberal. Let's say we'll look at clusters of 10 voxels and more. So you press enter, and then you get your contrast image. And so we can see here, this is avoid minus approach. So this is our second contrast. And you can see information here about the different brain blobs which show up. And it shows the p-value, p uncorrected. And then you can see K is the number of voxels. So we've got one blob of 95 voxels, another blob of 333 voxels, and then we have some smaller blobs. So this is a terrible, this visualization on this kind of glass brain is not really great. So to visualize better, you select overlays, sections, and then if you navigate to SPM12, canonical, single subject T1. Now that's remember your standard image, your standard structural image. So if you want to just put your brain activations over a standard image, then we can have a better idea of where these activations are in the brain. Click done, and then we see this nice brain image, and we can have a click around, and we can see here that we've got this in the approach, avoid minus approach contrast. We're seeing increased activations in these frontal areas. So it's quite interesting. If we look through the rest of the, so we're seeing that in the contrast of avoid minus approach, that we're seeing increased activation in these orbitofrontal regions. So we can also look at the other contrast that we defined. So if we want to go change contrast, we want to look at what the approach avoid contrast is. It will use the same stats as used before, and we see there are different brain regions in this that have greater activation in the approach decision minus the avoid decision. We'll similarly overlay it on the canonical. We've got not so much frontal activation. We have got some activation on the putamen and some small activation in the occipital lobe, but we're seeing less in the approach minus avoid condition. So that's just one subject. So one subject you wouldn't be writing a paper or reporting on, but it just gives you an idea of how you set up these contrasts, and these are the contrasts that you would later be grouping across many subjects for statistical tests of group differences or of mean activations across all subjects. So that's it for the first level analysis. Next we'll look at in the next time, we'll look at using more sophisticated motion parameter correction, and also how we would group this this first level data together to do group level statistics across either groups of patients and healthy controls, or looking at mean activation across a group.